Git. Some people love it, some people hate it, and some don't know much about it. If all you know about Git is git clone, git checkout, git pull, git push, this video is definitely for you. Today we're gonna deep dive into some advanced Git commands that are gonna definitely level up your version control game. We'll cover everything from managing large binary files with Git LFS to time traveling in your repository's history with Git reflog and Git filter repo. By the end of this video, you're gonna learn a ton of stuff about Git that the average software engineer does not know, even though they use Git on a day-to-day basis. As usual, buckle up. And with this video, it's definitely possible to follow along. So let's get started. So in order for you to follow along and in order for me to convey some of the more advanced concepts, we're going to need a repository to work with. And what better repository to use than the Git repository on GitHub? I'm going to create a fork of this repository and I'm going to put it in my personal profile. As you can see here, I've already created the fork, but this is how you do it if you want to do it on your own. You choose your profile, you keep everything as is, you untick this box because it's good to copy all of the different branches. You're going to have a lot to work with, and then you click on create fork. Once you do that, you're going to get a repository like this one, which is a fork from Git, as you can see over here. Now, you can do whatever you want with this repo. It's not going to be carried over upstream, and you're not going to embarrass yourself. So don't worry, this is a safe space to work with. The next step is for me to clone this repository locally so that I can work with it in my terminal. And I'm going to jump to my terminal over here, and then I'm going to run git clone, and then I'm going to provide the URL. Now, as you can see, I'm using SSH to authenticate. You can be using HTTPS. Doesn't matter. You could also use the GHCLI tool to copy the repository. I have a video on how GHCLI works. Go check it out if you don't know what that is. But for now, we're just going to clone this locally. You can see here we have only 382,000 objects. It's not a lot. I've seen a lot worse than this. And yeah, the clone happened very quickly. If we jump to Git, we will see that if we run git log one line, you will see that we have the entire history over here. So that's a good amount of stuff we can work with. Now, the first thing we're going to start with is to remove the remote push URL. Sometimes we're working in the repository where we want to avoid accidental pushes to GitHub, for example. And if you remember, you could type in your repo over here, git remote-v. This will show you the target as well as two URLs to which you can push and fetch from. Now, with Git, you can configure the fetch URL and the push URL to be different because you could be fetching from one repo and pushing to another. And you can have all sorts of variations to this. Now, let's say I want to avoid accidental pushes. So what I need to do is to remove this push URL, but retain the fetch URL because I want to fetch the updates, but not necessarily push changes. What I can do is git remote set URL -- push origin, and then specify this as an empty URL. Now, if I type in git remote -v again, you will see here that my push URL is empty, but my fetch URL stays the same. So now what I can do, if I do git pull, everything will work just fine. However, if I try to do a git push, it should effectively fail. Let's try this. Now let's make a small change, touch new file. This will create an empty file in my directory. Git add.git commit -m add new file, git push origin, and as you can see here, it's gonna fail with a fatal error, which is perfect, exactly what we need to do. The next command we're gonna talk about is git restore. Git restore was introduced as part of Git's command reorganization to provide clearer and more specific commands for different operations. Before git restore, and if you ask any boomer or very old millennial, well, there are no very old millennials, but older millennials, they will say that they used to use git reset or git checkout, and they don't know that git restore exists. But if you ask a lot of the more modern or younger software engineers, they would definitely be using git switch and git restore instead. Now, think of git restore as sort of your time machine for files. It serves three main purposes. One, discarding unwanted changes in your working directory. Number 2, unstaging files you accidentally staged. Number 3, bringing back files from any point in your repository's history. The key to understanding git restore is knowing the 3 main areas in Git. The working directory, where you added the files, the staging area, where you prepare changes for a commit, and your repository, for example, a GitHub repository, where you committed changes and where they are actually being stored remotely. Let me actually show you an example of that. So in our repo, we obviously have a readme.md file. Let's look for it. You can see it over here. What we're going to do is we're going to delete this. rm readme.md. It's gone. If we run git status, you will see that it's now not staged, but we could stage it for deletion. So right now, the file has just been removed. If we look for it again, we're not going to be able to find it. Now, what if we made this by mistake and we want to actually get that file back? You can type in git restore readme.md, and then it's back again. If we run the ls, you can see it over here. And if we run git status, you will notice that everything is back and everything is up to date or in sync with origin master, with the master branch in our target. The second variation of this command is to actually unstage a file that we have actually staged. So, for example, let's say I created a new file, touch new file. If I run git status, you will see that the file has been added, but it's unstaged because it's in red over here. So even if we do a git commit or a git push, nothing's going to happen because the file is not necessarily being tracked by Git. Now let's track it. So we can do git add new file. And then if we run git status again, you will see here that the new file has been staged and now it's in green. What if we did this staging by mistake and we want to restore that? What we can do is git restore -- staged and then specify new file. Now, if we run git status again, you will see here that the file is back in red and it has been unstaged. The last variation we want to talk about in git restore is the ability to restore files from a specific commit or branch or whatever other reference. We can do this as follows. First, let's identify some files that have been changed because I'm unfamiliar with this repo. Let's do the following. Git diff and then say name only and then specify that we want to find the changes from the 4th previous commit relative to the head. So 4 commits in the past. If we do this, you will see that the list of files are these, and one of the C files is blame.c. So this file has probably changed. Let's actually look at the changes from that version. We can do git diff head 4 and then specify, I think the file is in built-in, so built-in /blame.c. We can specify the file after the double dashes over here. And then you will see that, yes, indeed, we have a bunch of changes in between these 2 commits. So what if we want to restore the version from the 4th past commit? We can do the following. Git restore -- source equals. Here we can specify this in many different ways. I'm going to continue with my relative specification, head, then 4 previous commits from that point, and then specify the file we want to restore, built-in /blame.c. And as you can see here, if we run git status, the blame.c file has been modified. And the version it has been modified to is the version from 4 previous commits. So how can we verify that the file we have right now that is unstaged is the exact version that we got from 4 previous commits? We can run git diff, and then we can specify head to be 4 previous commits, and then we specify the file. And as you can see here, there are nothing pops because there are no changes. This is exactly the file that we have from 4 previous commits. And at this point in time, you can obviously, stage the file by doing git add built-in blame.c, and then obviously git commit restore from head relative 4. Obviously, you don't want this to be your commit message, but this is just demonstrating the process for you. And if you run git status again, you will notice that the local branch is 1 commit ahead of the upstream branch. Next up, we have git bundle. Now, git bundle is a powerful but often overlooked command that creates a single file containing everything needed to reconstruct a Git repository's history. Now, you need to think of it as a sophisticated export-import system for Git repos that maintains all the version control information and all the metadata. Now, why is a git bundle special? So unlike zip files, which you can generate or you can download from GitHub, for example, the bundle preserves the entire Git history, including all the commits, tags, and branches. And unlike cloning and pushing a repo, it works without network access. You can create the bundle, put it on a USB stick, move it to some other laptop, and pull from that bundle. And unlike copying the .git directory, you can obviously do that, the bundle is more portable and it can also be incrementally updated. So you have sort of a working copy of your repo that you can just move around. Now, git bundle works by creating a file that contains all the specified commits and their full history, all trees and blobs referenced by those commits, all the refs, branches, and tags pointing to those commits. Now, a few key concepts to understand. As a prerequisite for bundles, but the bundles need a common commit history between the source and the destination. And also, there are different bundle types. You can have a full bundle or you can have an incremental bundle where it contains only some specific changes or changes up to a specific point. And also, finally, bundles can be verified before by using actually git bundle verify. Let me show you how all of this stuff actually works. We have the fork of the git repo over here. Let's create a bundle. Git bundle create repo.bundle. We're going to call it repo.bundle, and we're going to specify the type to be everything. It's going to take a bit of time, but a bundle is going to be created right now from all of the objects, refs, whatever you need. And if you see here, if I run git status, you will see that I have the file repo.bundle available for me locally. Now, I can obviously move repo.bundle wherever I want. So let me do that. Move repo.bundle to, let's say, /projects/temp. Let me move it there. And as you can see here, it's been moved out. It's unstaged. For this next step, let me move to another directory entirely. So I'm going to move to my temp directory. And now I'm going to run git clone, but I'm going to clone from the bundle I just created. So let me do that. Git clone projects temp repo.bundle. And then I'm going to, specify the repo to be git. And as you can see here, the git clone actually works. And right now it's not actually pulling from GitHub or anything like that. It's creating an entirely working repository or a local copy from the bundle that I have right now. So if I go to the git folder over here, you will see that I'm now on the master branch. If I do a git log one line over here, you'll see that I have the entire history fully preserved from my bundle. Let me show you another way of using git bundle by creating a smaller bundle. Let's say I have made 5 distinct commits. Let's create a small for loop that runs from 1 to 5. Every time it creates a file, and then it appends the the cursor here to its name. It stages this file, and then it commits the file with a simple message, right? What this will do is we're just going to do 5 insertions. And if you can see here, these files have been committed. They have not been pushed upstream, but they're committed to my local copy or working copy. Now, I can run git bundle, and I can create a small bundle. So git bundle create, I'm going to call it small bundle. You can call it whatever you want. We're going to reference 5 commits from the master. And we're going to compare it to master. Now if I run this, you will see here now that I have a file called small bundle. If we do like we did before, and we move small bundle to another directory, and then if you remember, I cloned my git somewhere else in my temp directory as well. So let's go there. You will see here that I have no changes, right? And if I do a git log one line over here, it's pointing to git 2.48, no recent changes. So if I want to pull the changes from the bundle I just created, I can run the following: git pull, and then I can point to the bundle that I've created in my other temp folder. This one is called small bundle. And then I can specify the branch. And if I run this, you will see here that it has pulled the 5 files that were created from the for loop from the actual bundle. These have not been pulled from that other repo. They have been pulled from the bundle. And if I run git log one line, you will see here beyond 2.48, we have the 5 commits that have been added from that for loop. Pretty neat, huh? Next up, we have Git LFS, which stands for large file storage. Now, Git LFS solves one of Git's biggest limitations, which is the ability to handle large binary files. Now, to understand why Git LFS is important, let's first understand the problem. Traditional Git problems, with large files are one, repository bloat. Every version of every file is stored in every clone. You definitely don't want that, and you definitely don't want your repository size or the size of your .git folder to be, gigantic. You don't want it to be in the gigabytes, because this will slow down every single operation that Git actually needs to do. At the same time, Git needs to load all the objects into memory, and you definitely don't want to load a lot of, bloat and unnecessary binary files that are just not going to be useful when you're trying to do comparisons. And storage efficiency is another problem, because binary files obviously don't delta compress well. You cannot really compare or do a delta compression on binary files, because what you want to store is the variations between these files, not necessarily the files themselves. And because Git cannot really discover the differences between these binary files, it stores all the copies of these files. Git LFS solves these problems by replacing large files with small pointer files in the Git repository itself. And these pointers are for the binary file that gets uploaded to another or a separate LFS server. And then these files or large files are only downloaded when you need them. Now, the cool thing about Git LFS is that it supports streaming the download of large files, and it provides a very efficient way to cache them. If you can see here, this is the website of Git LFS, and this is the diagram that sort of represents what goes on. Whenever you have your local copy of the repository, and let's say this is the remote copy, which is GitHub, you can make code changes as many times as you want. But let's say you add a PSD file, which includes some designs for your website, and you want to push this. You obviously don't want to push this to your GitHub repository. What happens is with Git LFS, this file is uploaded to another large file storage. This could be anything. There are many companies that provide large file storage hosting services. GitHub also has some capacity for that, which is limited. I don't recall the number for that, but you can upload binary files to GitHub, and they are stored in the large file storage. What is happening in your local repo is that the file content is actually hashed. It is tracked also by Git LFS. The content is moved to LFS cache. The pointer file is created, which contains that particular hash. And when you commit the pointer instead of the original file. And then when you want to download, Git LFS will trigger. It will fetch these pointers. It will recognize where that file is stored, and it will download it from the actual source. Let me show you how all of this works in action. So here we are again in our trusted repository. Let's do the following. Let's take a screenshot of Git LFS over here. Let's save that locally. Let me move the file from my desktop, which is going to be this one, and let's move it locally. So if I run a git status, you will see here that I have a PNG. This PNG is how much in size? Let's do the following, grep.cs. It's about 334 kilobytes. Now, obviously, we don't want that to be committed. Now, first of all, you need to make sure that Git LFS is installed. If you're running on Mac or Ubuntu, you can run brew install git/lfs, or you can use aptitude with apt install git-lfs. On Windows, obviously, this works. You can just go to the gitlfs.com website and figure out the installation steps that belong to your system. Now, when you are in the repository and you want to use GitLFS for the first time, you have to also install it on that repo. If I do GitLFS install, it will basically update the Git hooks and it will initialize LFS. Why? Because the hooks, we're going to talk about them later on in this video, they're going to be responsible for figuring out when to deal with these files that are being tracked. Now also, what I want to do is I want to track the binary files, which are the images in this case. Sort of tracking is like staging them. So if I do the following, git lfs track anything dot, or let's put it in quotes, anything.png, you will see here that it says now it's tracking .png files. And what that means, if I put PNGs anywhere in my repository, it's going to be able to upload them to LFS instead of putting them in the repository on GitHub, along with all of the non-binary files. Now, if I do git status, you'll notice here that not only have I staged the .png in that I just copied, but it has also figured out that there are PNGs in other subdirectories that it could also add to the LFS storage, and it has modified the file .git attributes. Now, the .git attributes file is very important because this is where all of the tracking is contained, right? This is how you know that which type of files you are tracking to be uploaded using Git LFS. And if I check the content of the .git attributes, you will see here we have a bunch of other stuff that is also used separately by the Git repo, but we also have the .pngs, which are, calling, or we are specifying here that we want to use different tools to be able to run the diffs on them and to filter them and so on and so forth. And we want Git LFS to be able to upload these two separate files. Now, let's actually do the following. First, let's commit, or let's stage all the changes. Let's commit, enabling LFS and adding or committing images. Now, let's do the following. Git push origin. Now, obviously, git push is not going to work because we sort of messed it up in the first step of this video. Let's verify very quickly. Yep, indeed. Let's copy this one because we're going to use it to set the push URL. Git remote set URL push origin, and then instead of being empty, we're going to specify this one, and then we're going to run git push. Now, we're going to get another error here, which I'm going to explain in a second. Because we have forked the git repository, it's not going to allow us to push to LFS because this is a public fork. You just have to take my word on it that if you actually have another repository that you created yourself that is not a fork, in this case, the PNGs are going to be uploaded to another storage server, and they're not going to be stored alongside of your files, so that whenever you clone, you don't necessarily clone the whole thing, and it's not going to bog down your system. You're just going to be able to fetch the files when you actually need them. Let me show you how that actually looks like on the GitHub side. So we are on GitHub right now. This is a sample repository from another series of YouTube videos I made. And you can see here we have a demo GIF over here. And if I click on the demo.gif, you will see that it says here that it's stored with Git LFS. It's not stored with the Git repository itself. If you click on the help icon, you can read more about large files in the GitHub documentation. But yeah, this is pretty much how it works. If I go to the main repo, and if I go to the .git attributes, you will see here that I am actually tracking .gif files. They are filtered. The diff is managed by LFS and all of that fun stuff. That's Git LFS. Now we're going to talk about Git Bisect. So Git Bisect is a powerful debugging tool that helps you find the exact commit that introduced a bug by performing a binary search through your entire repository's history. Well, not entire, through the specified repository's history. It's like a systematic way of narrowing down where something went wrong. Git Bisect isn't useful in every single scenario. It's useful in sometimes the more complicated code bases, where a lot of changes are happening in parallel and there's a huge history, and you really want to chase down where a certain bug that is not necessarily easily discoverable lies. But Git Bisect also has some prerequisites. You need to be able to automatically test a problem. I mean, obviously you can use Git Bisect by manually doing tests to figure out whether a certain commit is working or failing. But if you have automatic tests or unit tests specifically, the process is so much easier. I'm going to show you that in a second. With Git Bisect, you mark certain commits are as bad, you mark certain commits are as good whenever you test and you don't find the bug. And then using binary search, the search space is going to shrink by half every time, so that you finally identify where the problem actually is. Let's go through a concrete example. So you can see here on my screen, I have VS Code that is running. This is Go. If you haven't written Go before, that's totally fine. This is an LLM generated code. I'm not going to bother in creating something much more complicated than this. It does the job. This is a pretty simple ticketing, algorithm or a process. We have a new ticket service that is going to be created. This ticket service has a base price, which is a float. The new ticket service, when it's being instantiated, we provide a base price as a parameter, and then that base price is set on the instance of the ticket service, and then we return a reference to that instance whenever we call new ticket service. Nothing really fancy over here. We are basically returning a pointer to the ticket service instance. Now, we have also a function that belongs to this ticket service. It's called calculate price. It takes as parameters an age and is student, a Boolean. And then the initial price is obviously the base price that we determine or that we set when we run our program. But then we start adding more discounts depending on the conditions that we have. So if the age is less than 10, that's a child, they get 50% off. If they are a senior, basically older than 70, they get a 30% off. If they are a student, they get an additional 20% off on the price. And finally, the mutated price over here is returned. It's as simple as that. The main function here is basically our main entry point. And this is where we create a new instance of the ticket service. We set the base price of the ticket to be $10. And then we provide a calculation call where we set the age to be 10 and say that this is not a student. We fetch the price and we return it. Now, the actual work is being done in the tests over here. The tests are pretty cool because this is how Go runs tests. This is the test definition over here. And we use something called tabulated tests. So think the couple of bracket pairs over here, each one of them is an actual test. So the first test is for a regular adult price. The base price is 10, the age is 30, they are not a student, and we expect the price to remain $10. We don't expect any errors. For the child, we expect the price to be cut in half, $5. For a senior, we expect the price to be cut by 30%, so we get $7. For the student, we expect the price to be cut by 20%, which means that this needs to be $8 instead of 10. And then for a student senior price, we expect the price to be 5.6 because they are a student and a senior. For the invalid age and invalid base price, we need to get an error. This is where we are running the tests. So nothing fancy. I'm going to run my terminal over here. And it's okay. Don't get bogged down by the Go code. It's not really necessary for you to understand it fully to reason about what's going to happen over here. I'm going to start by running my tests. And the way I would do that in Go is by calling this command, go test, and then specify where the tests are. And as you can see here, the tests are failing in a couple of places. Now, what I would like to know is which commit introduced this issue. In which commit are my tests actually start, or have my tests actually started failing? So let's look at the history of our repository over here. You can see here we have 5 commits. Currently, our head is pointed towards the main branch, and the main branch has this commit. So we have 1, 2, 3, 4, 5 commits since the beginning of this project. Keep this in mind. I'm going to take a screenshot of it. So let's take this one and let's put it here for our reference. Now, let's look at the terminal. Let's start the bisect process. We're going to do a git bisect start. And when we do that, it's going to start at this latest commit where the head is pointing at right now. Okay, and what we're going to do is we're going to try to specify which commits are good and which commits are bad. And the way we're going to know that is by running our tests. So I'm going to run go test one more time. We know that the tests are failing. So we're going to say git bisect bad. This is going to mark this commit over here as bad and that it's not functioning. Now we need to identify actually a good commit. So the way we would do that is by doing a git checkout. And when we want to do a git checkout, we need to specify which commit we want to jump to. So I'm going to jump to the initial commit because I really have no idea which one of these is actually good or bad. I want to maximize my chances of or increasing my search space as much as I can. And remember, in binary search, we're always cutting by half, right? So you're not going to really do a lot of steps. For these, probably it might take 2 or 3 steps max to find the issue. So we're going to do a git checkout of that initial commit SHA. And you can see here that we are now in a detached state, and that's okay. That means that the head is pointing to this particular SHA over here. Let me clear my screen and let's run go test. And you can see that the tests are actually working in this state. So what I'm going to do is I'm going to say git bisect good. Why? Because I'm pretty sure that this is working. What that means is git bisect has automatically jumped to this commit. So if you see here 725D0, that's the SHA of this commit over here in the middle. So binary search, obviously you should all know this, that it's gonna cut the search space in half. So it's gonna find the middle range, and that's gonna create the boundary for the new searching space, right? So the new searching space is gonna be between this commit and the beginning. So here, what we need to do is to run the tests one more time to identify whether there is a problem or not. Then obviously the problem remains. So we're going to say git bisect bad. And by doing that, sorry, I wrote go bisect, git bisect bad. And by doing that, you will notice that we reached the last step of the search, and it says that there are 0 revisions left after this particular one. And you will notice that we have also modified the SHA, or the commit that we are actually referencing or we're looking at, which is the 0AD0F88, and it's this one. Let me clear my screen one more time. Let's run the tests one more time. And in this case, the tests are actually working. So as you would expect, the bug is going to be introduced in this commit. So let's run git bisect and say that this is a good commit. And as you see here, the outcome has been identified. You will see that the commit that introduced the bug is 725, which is this one, D09A. And you will see here it says that this is the first bad commit. Fantastic. And it shows you which files have been changed, who was the author, which date, and what was the commit message for that. And here you can, now you can start working on a fix. You want to maybe remove all of that bad history. You want to squash it all together and combine it in the fix. It really depends. The solutions are various, but at least we identified where the problem has started. So now that we have reached the end of the bisect, we can say git bisect reset, and we will go back to the main branch. And this is not going to affect your repository in any way, shape, or form. It's not going to mutate your repository, so don't be afraid to run git bisect. It's not going to change any of your commits. It's not going to leave your repository in a bad state. And as you can see here, when you do git bisect reset, everything goes back to where it was at the beginning of your search. There's one more cool trick I want to show you with git bisect, which is that you can do all of the stuff I just showed you, but do it actually automatically. So the way you would go about it is by running git bisect start, but you wouldn't just run this like this. You would say head, and then you would also specify the range within which you want to do the git bisect. So you could say git bisect head and the 5C638AB commit. So it's going to do a git bisect on the same range we just did right now, but this one is going to be a bit more automatic. Why? Because we're going to do git bisect run, okay? And now we're going to specify here the command we want to run for testing. And this is going to be the go test. And you can see here that git bisect has automatically ran go test. And whenever go test returned, a failure, it marked the commit as bad. And whenever it returned a success, it marked the commit as good. And the final result is here. It's exactly the same result as we got. And it says here that this is the first bad commit, or the first commit that introduced the bad problem or the bug. And it's exactly the same result, which is 725D09A. So this is the power of automated testing. If you have these tests already written and you've invested the time in them, stuff like go bisect can be like super smooth, and it feels so good when something like git bisect actually identifies a problem for you. Great. Now we're going to talk about Git work trees. And Git work trees solve the challenge of working with multiple states of your repository simultaneously. So for example, if you're working on multiple feature branches, or you're working on your feature branch, but somebody comes in and says, hey, I found an issue with this particular release, and you really don't want to switch to another branch because you have a lot of unstaged files and things you didn't commit yet. You really don't want to mess that up. But you also, at the same time, you don't want to clone the entire repository all over again, because it can, sometimes if you're working in a big monolith, that can take a really long time. You really just want to check out a certain branch, but just put it in its own isolated directory and work with it. This is something that work trees do brilliantly. They basically allow you to retain the main repository, which contains the original .git directory, that will still work as a reference repository, and it's going to manage all the objects and refs. However, the linked work trees will have their own working directory. There is a lock system that prevents multiple work trees from checking out the same branch, and it also ensures the data safety across your work trees and manages the ref updates atomically. Let's show you exactly how work trees operate, or how you can actually use and manage your work trees in our Git repository. So in our Git repository, if I do Git branches, you will see here that I have a bunch of branches that are remote, and I have my master branch. Let's say I'm working in the master branch. Just humor me here. Somebody comes in and says, hey, in the next branch, we have an issue that we need to resolve. So what you can actually do is run git work tree add and specify where you want to add it. So let's say I want to add it in the feature next, let's call it. And then you specify now what is the name of the branch. So this is the name of the folder that you want to put the work directory in. And this is the name of the branch over here. When you do that, it's going to prepare the work tree. And you see here that it's pointing to this particular commit. If you see here, when I ran git status, a new folder was created. Obviously, that's what we want. And if I go to that folder, you will see that I have the entire working directory with all of the files, but these are coming from the next branch. So if I want to go back to the previous one, I just go to the previous repo. If I want to work in the next branch, I just go to feature next. And this is like feature complete. You can easily do file changes, let's say file 1, and then you can stage these files. You can commit these files. You can push and pull from the remote repo. You can do anything you would normally do with a branch, but it's just going to be, specific in your working tree or new working directory. I'm going to commit this, let's say adding a new file. I just want to show you that it doesn't really affect the other stuff. And then I'm going to do a git log, one line. So again, I'm in my feature directory in my work tree. And then you can see here that I am a couple of commits. Sorry, not a couple, just one. I just added this new file over here. But if I go back to the previous directory and run git log one line, you will see that I'm still pointing to, the master branch. Nothing has changed. The one thing important is that you shouldn't really commit your work tree. So you can list the work trees that you currently have and which directory they are in by running git work tree list, as I did over here. You can see it. And when you're done with a certain work tree, you can say git work tree remove and then specify the directories. In this case, it's going to be feature next or the full path, whatever works. And then if you run git work tree list one more time, you will see that I only have one work tree, which is pointing to my master branch. Git work trees are awesome. I often use them whenever switching branches doesn't make a lot of sense. And they could be pretty useful for your workflow as well. It's good for you to know them. Another cool Git feature that I make use of a lot is Git hooks. Git hooks are scripts that Git can execute automatically before or after specific events in your repository. They're like event listeners for your Git workflow. They allow you to inject custom behavior and enforce certain policies at critical points in the development process. Now, for you to understand how Git hooks work, they have two timings, a pre-hook or a post-hook. A pre-hook runs before a certain action, or it can prevent an action from happening if the hook fails. And the post hook, it runs after an action. If you want to, send a notification or trigger something else after that action has been done. Now, there are two types of hooks as well. The client-side hooks and there's the server-side hooks. Client-side hooks is basically in your local, working directory, in your local Git repository that you just have cloned on your machine. This is where the hooks are. You have many of them. You have pre-commit hooks before a commit is created, pre-commit message before the commit message editor is open. You have the commit message that can do validation on commit messages, post-commit after the commit has been completed, pre-rebase, post-checkout, post-merge, pre-push, all sorts of stuff. But you also have server-side hooks. And server-side hooks are basically created on the receiving end. So when you push a change somewhere else to another target, this is when the hook is created. So there's the pre-receive hook whenever it's triggered before accepting a certain push. There's the update hook where, it does pre-branch push validation. There's also post-receive. So after the entire push is completed, that hook is triggered or that script starts running. For the implementation, let's have a look at our repository again. All of the hooks are located in the folder .git. So again, remember, we are in our Git repo or working directory here. So if you go to the .git folder, don't be intimidated by this folder. There's a lot of cool stuff in here. If you go to the folder hooks and you do a listing, you will see that we have samples of all of the hooks that we could actually use. So you will notice that the samples have .sample at the end. And you will also notice that all of these files are actually executable. So you have the X over here, and it's very important. A hook will not be triggered unless it is an executable. So be careful of that. And if you actually want to activate a certain hook, you just need to remove the .sample from the end, and then it will be a script that can actually run. So you will see here the post merge, for example. This is an actual hook. Let's see the content. So if I do a bat post merge, and by the way, bat is just a variation on cat. It just does nice coloring and formatting. So you'll see here in the post merge, we are running the command git lfs. Now, normally in your repo, you should not see this because you did not install git lfs unless you were following along this tutorial and you installed git lfs. So now you understand how git lfs works. Git lfs is actually a bunch of hooks that are on the post checkout, post commit, post merge, and they do the work for you after these events happen. So after you check out something, after you commit something, after you merge something, this triggers git lfs on your behalf, and then you get an echoing of certain messages that stuff was not found or found, and then you have an exit with an exit code. And if you don't understand what exit codes are in the context of Linux, I have an entire video dedicated for understanding bash internals and understanding how a lot of the Linux scripting works, which is a highly recommended video. I highly recommend for you to go and watch that one. It's a deep dive and it's really awesome. If we want to do a pre-commit hook, let's actually do one. Why not? Or maybe a pre-push. Let's make a pre-commit hook. I'm gonna move the pre-commit .sample, which basically is renaming it, and I'm gonna rename it to just pre-commit. Now let's open the pre-commit file in Vim, and you can already see that we have a bunch of stuff, which in my opinion, we're not gonna need for now. So I'm just gonna do a visual block selection, go to the end, capital insert, done. We commented them all out, and now we're gonna write our own script. So you can do whatever you want. You can add any condition, just write a regular bash script over here, or it can be anything else. Like you can just change the shebang to maybe it could be Python or PHP or whatever else, or Ruby or whatever, anything else you're comfortable with, as long as it is an executable. So what we're gonna do here is we're gonna just say echo, hey, from the pre-commit hook. That's it, and then we're gonna exit with 0. It's very important that you exit with the right exit code, because otherwise, if the exit code is 1 or higher, that means this is a failure, and then it's not gonna allow you to commit your change, right? So what we actually want is just to echo this stuff and exit successfully so that the commit goes through. The pre-commit hooks are very important because they can block certain actions from happening. And in this case, it's going to block the commit from happening. Sorry, that was unintended. All right, let's save and close the file. Now we go back to our repository and let's say touch new file and then git add. And then we're going to say git commit adding new file. And when I do that, what do you see here? The message. Why? Because the hook was triggered before the commit event actually took place. And that's exactly what we want. So you can use the hooks to do all sorts of stuff. Maybe you could use the hook to run a linter. Maybe you could use the hook to run tests. Maybe you could use the hook to run, I don't know, whatever else you want before a commit actually happens. This is a good mechanism. Now, one thing to remember here is that even if you change these files, and you commit changes and you push them upstream, the hooks are not going to be moved with your changes. So the hook changes you introduce on a working copy, like over here, are local changes. This is very important. So if you want everybody on your team to implement the same hooks, you have to figure out another mechanism for that. Some people use a third-party tool that comes in and installs certain hooks for them, or you can just distribute the hooks in another form. It's really up to you how you manage those. Now you know that they exist, and now you know that they work. Feel free to use them. Now let's talk about the interactive batch staging with Git, which is basically calling git add -p or --patch. This option transforms Git's staging area from a file level tool into a change level tool. This allows you basically to stage specific changes within the same file rather than entire files completely. So you can cherry pick and you can, well, cherry pick is not the right choice of words here, but you can select which changes you want to stage and not necessarily have to do the entire file. Now, this is really cool. Why? Because that allows you to create more logical commits. So when people say, make sure that you construct your commits in a way that they are sort of coherent, the changes in these commits they make sense together, you want to make them a little bit more atomic, that's how you can achieve that particular result. Now, with patch mode, there are stuff that are called hunks, which is basically the chunk of change. The chunk of change, you can make it bigger, smaller, you can split it if it's too large, you can manually edit it. You know, it's contextual to the surrounding lines, and it's an atomic unit of change, basically. That's how you need to look at it. And then you can have in the same commit multiple hunks from multiple files. You can, pick and choose whatever you want or however you want to structure your document. So let's make this a little bit more concrete. Let's go back to our git bisect repo, and let's go back to basically the ticket service. Now, in the ticket service, I've introduced a bunch of changes. So I introduced the change over here on line 10, where I introduced the discounted price. I also made a change over here where I return now as part of the instance the discounted price in addition to the base price. I also made the change here where I'm applying an additional 2% discount for everybody. And I have made some changes here where I'm printing an extra price for the 25-year-old student. Okay, so the changes that are at the top of the file over here, they make sense to be combined or to be together. So the change of the discounted price being added, this and this, they make sense to be together. They make sense to be a single commit because I'm introducing a new concept. However, adding this over here might or might not make sense. Maybe you want to keep it for another commit, right? And then eventually making this print call, which is effectively sort of a test, is also maybe you want to stage it, maybe you don't want to stage it at all. You can get the choice of that. So normally what people do is they would just add the entire file. But now what we actually want to do is to be able to stage certain chunks of it. So let's see how that works. Git add -p, and when we do that, we start seeing the difference. So here is the output of the diff. It tells us that this is the first file that has dashes, and this is the second, or the change that we made, which has the pluses, and this is the delta, the difference, right? And the delta is we have discounted price over here, and we have this. Now, this hunk, as it has been identified by Git, actually makes sense, to be honest. Like, I definitely want this stuff to be together. So you have here the list of commands that you can actually run. So Y means stage this hunk, N means skip it, Q means quit the stage, A means stage this and all the other remaining hunks, so basically stage everything, and by that, basically staging the whole file, which we don't necessarily want. D is skip this and all the other remaining hunks. Then we have S, which means split, and then E means manual. And for the rest, I'm not really sure what they are. And you can also obviously check you can run the exclamation mark to get the list of all of the other possible other options. So what we're going to do here is we are actually going to type yes, because I actually want to add this hunk, but I don't want this one. So I'm just going to skip it with an N. I don't want this change as well, and I'm going to skip it with an N. Once you're done, if you run git status, you will see that the main.go file has been modified. So what I'm going to do now is I'm going to commit this change. Remember, don't do a git add because you already staged the change. And then I'm going to say here, add discounted price. And this is really cool because if I run a git diff now, you will see that the commit says adding discounted price. And if I look at the change, yes, it's very much related to just adding a discounted price instead of it being a bunch of other stuff that also does not make sense or relate to the commit message that we have just included. And with this mechanism, you can make your commits much more granular, much more specific, and then you don't have to worry about commit messages anymore not really making sense because you have a lot of different changes. That's how professional software engineers do it. Now let's talk about Git's ability to do patch management and how you can get a diff, create a patch from it, and then send that patch to somebody that they can apply on their own, version or working copy of the repository. And you don't necessarily need GitHub to be in the middle of it all. You don't need a pull request and you don't need all of that other stuff, because that's how building the Linux kernel works. People just send patches over email to each other, and then they apply these patches, run the tests, and manage the whole change pretty much like that. That's how it works. There's a Git has an ability to come up with a diff, and it has apply commands. They create a powerful system for sharing and applying changes between repos, even between different versions of control systems sometimes. This combination allows for, fine-grained control over how changes are shared and they are integrated or introduced to different repositories. Let me show you an example of how that works with our Git bisect repository over here, because we want to keep it a bit simple. Let's do the following. We have the bunch of changes. So if you see here, we introduced the price, we introduced the output of the calculated price, and I want this change to carry it over to another copy, maybe to a colleague. I want to send it via a gist or via email or whatever it is. I can create a patch out of this diff. So I can say git diff, and then I can name the patch. Let's say add price dot patch. What that will do is it will create a new file for me. It's called addPrice.patch, 595 bytes in size. If I read the content of the add, you will see that this is the diff, basically, the diff output, which is stored in that patch file. Nothing really super out of the ordinary over here. Now, if I open another tab over here, not tab, this is a slice of the window in Tmux, and I go to a git bisect copy. So this is basically a copy of the git bisect working project over here. Obviously you wouldn't do it like this on the same machine. Maybe you would, actually, who knows, you might have a scenario for it, or a couple of copies of the same repo and you want to carry changes over this way. It's a way. What you would do is you would need to copy the patch from the other repository by sending it somehow. Let's say git bisect, and we called it addPrice.patch. So we're just gonna copy it over, or you can just simply apply it directly. You don't need to even copy it. So let's do git apply, and then we're gonna apply this patch. And then when we do git status, you'll notice here that the file that has been modified is main.go. And if I run git diff, you will also see that the changes have just automatically been applied from the other repository or from this patch that we have over here. Pretty simple, pretty neat. This is how you can carry change over multiple repositories. Git is a very elegant tool, I know. Well, this video has been quite a journey, but we still have 3 more concepts to go. First one is git reflog. Git reflog is basically your repository's detailed diary. It records every change to branch tips and other references. It's basically your safety net for recovering from catastrophic mistakes to your working local copy. Obviously, the junior engineers will basically delete the entire repo, clone it all over again. The more advanced engineers will definitely learn how to spend more time, or you should learn how to spend more time in your reflog. Now, what gets recorded into the reflog? Every head movement, when you check out a branch, when you switch branches and whatnot, this is a head movement. Branch creation and deletion is another thing that gets recorded. When you do a git reset or git restore, these reset operations are recorded. When you do rebase or merge operations, and then any command that updates the refs by creating new tags, deleting tags, so on and so forth, all of that goes into the reflog. Let's have a look at the reflog. And let's try to restore a certain state in our repository. If we do a git log one line, you will see that this is it. This is the clean repo as you would have expected to be. But if we run git reflog, you will see that there's a lot more that was done to this repository since we started this video, right? We did a lot of different changes. We have some commits over here. We actually did a bunch of resets. You can see here we moved from, we moved to the origin master. I did the reset because I wanted to reset the repo. I think I also switched to the branch next. I think it should be somewhere. Let me try to find it. There we go, moving from master to next. So when you also do branch switches, you can also see them here. Now, let's say I want to move back to this state over here, or maybe even this state. Why would I not pick this one? Maybe this commit is no longer in my tree anymore, right? Maybe this was an intermediary state. It got deleted. It got lost. We did all sorts of other rebasing stuff, and we lost this change. Maybe we squashed a bunch of stuff and they're no longer there. So what I'm going to do here is I'm going to copy head at 10, and then I'm going to exit. Then I'm going to do a git reset hard this time. And I'm going to specify hit 10. And you can see here immediately the head has switched to this particular SHA, and the commit message is adding 4. And if I do a git log one line, you will see that the history has also changed. And now I'm in this intermediary state where I'm adding the 4th file. If you remember from a previous step in this video, we added 5 files with a for loop. So I'm adding the 4th file over here, and I reset my entire repo to that state. If I run git reflog again, you will notice here that there's a bunch of stuff that has happened, and you will see that we did a reset by moving to head number 10. Now, be very careful when you're working with the reflog. You could end up in a state where you cannot really recover the latest in your repo. What I would normally recommend is you grab a copy of the working directory, or grab a copy of your entire repo, put it somewhere else, work with the reflog, validate your changes, do whatever you need to do, and always maintain a backup. Sometimes, even if you are, as experienced as much as possible with these things, you could end up in a state where you mess things up and you are not able to recover from the reflog even anymore. So be careful when you use these tools. That's it. Let's say you want to recover a deleted branch. You can also do a git checkout -b. Name of the branch, and you can also point, for example, head 6, let's say, and this will basically create a new branch, and it will, let's see, git log one line. It will basically move you back to head number 6, whatever that entry was pointing to, basically. That's it. That's all you need to know. These are the basics of using the reflog. Before we jump to talk about history rewrites, let's talk about Git for each ref. Git for each ref is a Swiss Army knife for repository reference analysis and automation. It provides a powerful way to query and format information about refs. Refs basically are, branches, tags, remote references in your particular repository. Now, what you need to know is that local branches are designated as refs heads / star or whatever. And then remote branches will be refs remotes / the name of your remote branch. Tags will look as refs tags / star. Okay. And then you might have notes. Notes will look like refs notes and the name of your note. It could be whatever it is. Now, how can you use this? Let's take some more concrete examples. Let's say you want to list all of the branches with their latest commit date. So you have a bunch of branches in your repo. In this particular case, let me show you git branches. By the way, git branches here is an alias. What you would want is git branch -l. We have 3 branches, but we also have remote branches. So let's run this command and see the output. You will see here that git for each ref ran, and then we specified that we want to sort by the committer date. We want the refs heads, right? So we just want the local branches. And then we specified the format. We want the committer date to be short and we want the ref name to be short. We can also add more stuff to it. So let's actually do something like this. Okay, maybe I want the subject to be here and let's add a column, let's say. So now you have the latest commits with the subjects for each particular branch. Pretty handy, if you ask me. You have another option. So for this next one, we want to count the number of commits in each branch or in each local branch that we have. And for that, we just call git for each ref. We specify the format to have a short ref name. And then we want to also query the local branch, as we said. Then we're going to pass all of this input to the while loop, which is going to iterate over the different branches. And then for each one of the branches, it's going to make a call to git rev list. So this is not just for each ref only, we're also leveraging rev list to count the number of commits in each branch. And when we run this, you will see that we have, 75,000 commits in the master branch. We have 76,000 in the next branch. And this one is a copy of the next branch. That's why you also see that it has one less commit. I made some local changes over here. So that's another way of using the git for each ref. You might also maybe want to show the branches and their upstream status. So basically the local branches and what's the status of the remote branches. You can do that with git for each ref. You specify the format. This is the local branch. This is the upstream, right? And then you want to see if it's ahead or behind. And then you can call the track over here for each one of these. And then when you call it, you will see that, for example, all of these are fine except the next. The next is ahead by 1 commit. So locally, I have introduced a change that is not yet in the remote branch. That's it. I think this is a great start to for each ref, and it's pretty handy too. And for the very last part of this video, we're going to talk about history rewriting. A lot of the problems that you're going to face with your repository, like if somebody makes a bad commit or commits the wrong file or whatever, you can resolve them with a reset. You can also resolve them with a sort of a rebase sometimes. If you want to change the commit message or the commit, if you want to bundle a bunch of commits together. However, sometimes somebody makes a very severe problematic change. And let's say they commit a password file that goes undetected for so many commits afterwards. And this file exists in so many different refs. And it's extremely difficult to clean it at that point in time. Sometimes I've seen the history rewrite happen when we're trying to migrate repositories that have been plagued with binary files that are quite gigantic and that need removal before they can be migrated to, for example, GitHub repositories and whatnot. We're not going to deal with a lot of the complicated scenarios in this section. We're just going to talk a little bit about how you can rewrite Git's history. Because rewriting a history, it's not easy. You have to go through all of the different commits, make whatever changes that are necessary, and then recommit them again. And when you recommit them again, you're not going to be able to retain the same SHA for the commits. Obviously, the commits are going to be assigned to new SHAs. Now, there are tools to help you with that. And one of these tools is the Git filter branch. However, the Git filter branch, which comes pre-bundled with Git, has a lot of gotchas and it has a lot of problems that can make rewriting the history even more complicated than what it actually should be. Like, this is a list of all of the different safety concerns and problems that might arise from the usage of Git filter branch, like file names with no spaces are mishandled, non-ASCII file names can be silently removed, despite them being in the desired directory. And you obviously don't want to deal with a whole world of unknowns. A history rewrite is complicated enough all by its own, and you definitely need a tool that is safer to deal with that. That's why the Git project now recommends the usage of this Python utility, which is called Git filter repo. Git filter repo is maintained separately, and you can download your own copy of it. You can use Homebrew, or you can use Aptitude or pip even, because it's a Python script. You can see it over here. And a Git filter repo does the history rewrite for you. It's way faster than Git filter branch, and it can make really complicated scenarios much simpler to deal with. Like, for example, here's one. This is an example of extracting a piece of a repository with the intent of merging just that piece into a bigger repository. And obviously, when you want to extract that piece, you just don't want to move the files only, but you also want to move the history related to that particular directory, for example. Obviously, now you think about it, this is going really deep into the internals of Git. And then you're going to have to move all of the different objects, the different commit messages. You have to relink the SHAs where appropriate. And then if you have different branches and refs and whatnot, you have to carry all of that over. So with Git filter branch, you can actually do this with just this one command. And that's it, problem solved. There's another tool called BFG Repo Cleaner, but it's very old, very legacy. You definitely don't want to deal with that. And with Git filter branch, this is what the work actually looks like. And quite frankly, unless you're like knee deep in the plumbing of Git, you definitely don't want to deal with this stuff. Now, for this video that we're making, let's take a couple of simpler examples. So one of the examples is going to be that we are going to delete a file from all of the history. Let's assume it's a password file. It's an env file with a bunch of passwords that has polluted our history. We're going to see how we can deal with that. And another one is a bit more fun, where we're going to change the author name and email in our test repository. So let's actually go through both of them. We have our trusted Git repo over here. We're going to play around with this one because this is a copy of the actual repo. And as always, these are very destructive tools that you cannot recover from. There's no undo for, Git filter repo. So make sure you know what you're doing. And if not, work on even if you know what you're doing, actually work on a backup of the repo. Because again, these are dangerous and very destructive. So the first thing we're going to do is, let's pick a file. Let's say version.c. I'm pretty sure version.c has been in this project since the beginning. So the way we're going to deal with that, or we're going to remove it not just from this and commit the change, we're going to remove it from the entire history as if it never existed. We're going to run git filter repo, and then we're going to say path version.c invert paths. That's it. Now it's going to go over all of the commits in this particular project or in this particular repo. It's going to delete that file. It's going to make new commits. I'm going to show you in a second the mapping between the old and the new commits. And it's going to just expunge it as if it never, ever was ever introduced to the repo. And quite frankly, for 75,000 commits, that's pretty fast. Now, there are bigger repositories out there, obviously, with millions of commits, gigantic sizes, innumerable objects. This process can take way much longer, but 39 seconds is pretty decent to expunge a file, from the history of a repo. And now if we do if we run this, you will see that version.c no longer exists. Let's verify this in a better way. So if we do listing grep version.c, let's wrap it. Actually, it's better. There's no version.c. We can do git log all and then full history. And then we can do version.c. You're not gonna find it. Let's show you that it actually works. Let's pick another file, maybe version.h, because these are obviously gonna be related. So let's do this instead. And as you can see, this will show you all of the different commits where this file was modified or changed or introduced. So version.c is no longer in the history. If we go to the Git folder and we do a listing, you will see that we have a folder called filter repo. If you go into filter repo, it will show you the outcome of the change that we have introduced. So for example, if we go into the commit map, it will show you the previous commits as well as the new commits that were created as a result of the change. So this is how you can keep track of what was modified, and it will also sometimes list the problems that it might have. And yeah, this is pretty much it for the file deletion. Honestly, it's pretty simple for deleting a single file. For more complicated scenarios, I'm not saying it's going to be always super simple. Sometimes it can get pretty complicated. So for the fun part of this history rewrite, we are going to take credit for building Git instead of Linus Torvalds. So what we're going to do here is we're going to fetch the Git log. We're going to specify the author to be Linus, and then we're going to reverse that order. And as you can see here, this is pretty much the first commit that was made using Git on Thursday, April 7, 2005. And this was the author. He used this email address as well as his actual name as the author of this commit. So what we're going to do is we're going to sort of rewrite history and hijack Linus's work. We're going to do that with git filter repo. The command is pretty long. It's not very complicated, but I just already wrote it down for speed. So what this will do is it will call commit callback. And for each one of the commits, it's going to run this Python script, which is in between single quotes. And then it's going to define an old email, the corrected name, corrected email. And then if the committer email is equal to the old one, it's going to replace it. And if the author email is equal to the old email, it's going to replace the author. That's it. It's as simple as that. Now we're going to run this. Of course, it's going to complain because this is not a fresh copy or a mirrored copy of the repo. There's actually in the documentation a way to cleanly fetch your repository for git filter repo to work. This is sort of a safety gate, but I'm going to bypass it right now because, again, we're just doing it for fun. So here we go. This is going to go over all of the 75,000 whatever commits, and it's going to rewrite them. I'm going to show you the output in just a second. That's it. We're done. 38 seconds again, or almost 39 seconds. And now if we run this command over here, you will see that now the commits from Linus have been hijacked by some other author. And now my name is all over the repository instead. That's it. That's pretty much everything I wanted to show you about Git filter repo. I hope you learned a thing or two. And again, please use these tools safely. That's it. That's our Git deep dive wrapped up. I'm pretty happy about the outcome of this video. If you notice the timestamps, it took me a long time to shoot this video, pretty much the entire day almost, because it's sometimes very difficult to stage some of the more complicated examples. You know, mistakes happen, and then you have to sort of figure out a way to repeat all of the different steps, reset the repository to a state that it was before, and it can be a little bit tricky. Anyway, I'm very happy that this deep dive is done. I hope you learned something interesting. Congratulations on becoming a Git expert. You probably know by now way more than the average Git user. Use this knowledge wisely, and I hope it helps you throughout your journey as a software engineer. Thank you very much again for watching yet another video. Thank you for your support. I would love if you like, comment on this video, share it with your fellow colleagues or people you think should know a little bit more about Git. don't forget to subscribe to this channel. And if you become a member, you're gonna get early access to a lot of this type of videos and some exclusives that are only available for members. Thank you all, and I'll catch you next time.